Today we are going to discuss about boiling and boiling regimes. In this topic, we have to discuss differentiate between evaporation and boiling, and gain familiarity with the different types of boiling. Develop a good understanding of the boiling curve, in which you can see boiling regions, that is boiling regimes. The different boiling regimes corresponding to different regions of the boiling curve. Also, we can discuss about various regions familiarity. We are going to discuss the various heat transfer processes in boiling. What is meant by boiling? The transition of a liquid into vapor. In this section, we have many of you are confused about evaporation and boiling. In the case of evaporation, it occurs at the liquid vapor interface when the vapor pressure is less than the saturation pressure of the liquid at a given temperature. At that time, boiling occurs at the solid liquid interface. You should underline these two words: liquid vapor interface and solid liquid interface. In the case of evaporation, it is in liquid vapor interface. In the case of boiling, it is in solid liquid interface. Boiling, when a liquid is brought into contact with the surface maintained at a temperature sufficiently above the saturation temperature of the liquid. So both are not same. Next is how to keep a liquid boiling. The heat that is expended in the formation of bubbles must be supplied. Boiling is associated with the transformation of liquid to vapor. In both these cases, special form of Newton's law of cooling is applicable. Okay, here all of you know Newton's law of cooling states that heat transfer rate is equal to H delta T, where H is enthalpy and delta T means delta T excess temperature, where the difference between surface temperature and saturation temperature of the liquid. Okay, there are classification of boiling. Next is classification of boiling. In this section, we are considering pool boiling, flow boiling, subcooled boiling, and saturated boiling. While we are classifying the boiling, in the case of pool boiling is called pool boiling in the absence of bulk fluid flow. Any motion of the fluid is due to the natural convection currents and the motion of the bubbles under the influence of buoyancy. At that time, in case of flow boiling, it is in the presence of bulk fluid flow. In flow boiling, the fluid is forced to move in a heated pipe or over a surface by external means such as a pump. Okay. At the time, subcooled boiling, where when the temperature of the main body of the liquid is below the saturation temperature, it is known as subcooled boiling. At that time, when the temperature of the liquid is equal to the saturation temperature, it is known as saturated boiling. Okay, here the liquid temperature is slightly larger than saturation temperature. Next is special cases in boiling: pool boiling, forced convection, saturated boiling, and subcooled boiling. Okay. Next is about the boiling curve, which shows the boiling regimes, otherwise boiling regions. You can see a plot in which Q, that is heat transfer rate, heat flux, that is watt per meter square, versus excess temperature difference. Okay, this plot is known as boiling curve. Here you can see A to B, which is pure convection with liquid rising to surface for evaporation. In the case of B to C, here it is a nucleate boiling, B to C and C to D both are under nucleate boiling, but B to C is nucleate boiling with the bubbles condensing in liquid, whereas in C to D, nucleate boiling with the bubbles rising to surface. At D it is peak temperature. D to E, the partial nucleate boiling and unstable film boiling. There is a trend towards the film boiling starts at D to E. At E, film boiling is stabilized. So E to F, radiation becomes a dominant mechanism for heat transfer. So while we are considering each section, that is first A to B, the free convection boiling section, there little vapor formation is there. Liquid motion is principally due to a single phase natural convection. Then onset nucleate boiling, that is nucleate boiling from starts at B. So after that, isolated vapor bubbles will be there. Liquid motion is strongly influenced by nucleation of bubbles at the surface up to C only. Then after C, that is 10 degrees Celsius, above 10 degrees Celsius, excess temperature difference is above 10 degrees Celsius. There below 30 degrees Celsius, it is known as jets and columns. Increasing numbers of nucleation sites causes bubble interaction, and jets and slugs are there. We can visually see this bubble interaction while we are experimenting. Here liquid in surface contact is impaired. Next is D, the peak temperature. At that time, critical heat flux is there. Maximum attainable heat flux in nucleate boiling is occurring here. After that, potential burn out of power controlled heating occurs. Okay, in between D to E. At E starts the film boiling, where the heat transfer is by conduction and radiation across the vapor blanket. Reduction in heat flux occurs, follows the cooling curve, but it is, we cannot correctly show this portion, film boiling portion. Then you can see the detailed plot boiling curve here. As I already mentioned, A to B, B to C, C to D, D to E are the main regions. Up to A, it is natural convection boiling, where already I told that bubbles do not form on the heating surface until the liquid is heated a few degrees above the saturation temperature. The liquid is slightly superheated in this case, metastable state. So the fluid motion in this mode of boiling is governed by natural convection currents. Heat transfer from the heating surface to the fluid is by natural convection. Next, the case is nucleate boiling from A to C, where region AB is isolated bubbles. The bubbles form at an increasing rate, at an increasing number of nucleation sites as we move along the boiling curve toward point C. Okay, at region BC, the numerous continuous columns of vapor in the liquid. Okay, next is while in the main difference between A to B and B to C are the bubble formation and bubble interaction. Okay, at D it is critical or maximum heat flux. It is of higher importance. C, the point C, it is critical or maximum heat flux. It is of prime engineering importance. Okay, after that, transition boiling will occur between C to D, where delta T, that is excess temperature difference, is increased past point C. The heat flux decreases. This is because a large fraction of the heater surface is covered by a vapor film, which acts as an insulation. It is important. In the transition boiling regime, both nucleate and boiling partially occur. Okay, we can see the various regimes listed out here, and I told the first section, second section both A to B and B to C, again C to D. Okay, then finally D and D to E, where the film boiling occurs. Beyond point D, the heater surface is completely covered by a continuous stable vapor film. At point D, where the heat flux reaches a minimum, is called the Leidenfrost point. You can see here. Okay, here. The presence of the vapor film between the heater surface and the liquid is responsible for the low heat transfer rates in the flow boiling region. The heat transfer rate increases with increasing excess temperature due to radiation to the liquid. So as I told about the burnout phenomenon, you cannot typically we cannot follow the boiling curve on this burnout phenomenon. That is, C after C there is sudden jump in temperature, you can see. So when the power applied to the heated surface exceeded the value at point C even slightly, the surface temperature increased suddenly to point E. You can see the point E there. When the power is reduced gradually starting from point E, the cooling curve follows this figure with a sudden drop in excess temperature when point D is reached. Okay, you can see it will come like this. This is the problem. Heat transfer correlations are there, different correlations are there. It is beyond our syllabus. Okay, thank you.